Hello, good morning, good afternoon, good evening for our friends around the world. Super excited to have our webinar today, how to efficiently build custom LLMs on your data with the newly launched Ludwig 0.8. A lot of really cool features we're going to show you around fine tuning and other capabilities. We have our two awesome speakers with us. We have a great crowd here, so we're just going to kick things off and get going and make the most use of the time. You'll notice, by the way, in the sidebar, I just posted the link to the notebooks that we'll be covering today, so you can follow along and let us, say hello and let us know where you're from. And let's get started. My name is Michael Ortega. I lead marketing at Predabase. I'll be your host today. A few just quick logistics for folks who are tuning in. One reminder, the lines are muted except for our speakers, but we love for the session to be interactive. And so what I recommend or ask is that folks post their questions into the chat bar on the side. You can post them throughout the session. We'll have some Predabasers on who will answer some of those questions, but we'll also do a live Q&A at the end, and at which point we'll answer any of your detailed questions. And any questions we don't get to, we'll follow up after. As a reminder, this is an interactive and follow along session, so there are notebooks today. If you want to get into Ludwig 0.8 and follow the great session Arnav's doing, you can download them. There's a link here and also in the chat, and also push out a link. Let me do it right now as a featured action for everybody. And here we go. Here's also a button that'll pop up. If you want to learn more about Ludwig, the package, and also 0.8, you can go to ludwig.ai. We also have a link to the Slack community. You can join in. We're always looking for contributors to participate in this great open source project. And of course, if you're looking for a hosted LLM solution where you can instantly deploy, prompt, and start to fine tune your own LLMs in your own environment, you can also try Predabase for free with our free trial, and there's a link there as well. All right, a quick introduction for our speakers today. We have with us joining Piero, who is the founder and CEO, or co-founder and CEO of Predabase, also the original creator of Ludwig. Ludwig was created while he was at Uber. He'll talk about that a little bit, where Piero was a founding member of the Uber AI organization. Also joining Piero is machine learning engineer at Predabase, Arnav. Arnav leads many of our initiatives here, working on scalable ML infrastructure, some of the new LM capabilities around things like fine tuning, but he's also a lead maintainer on the Ludwig project. So I can't think of any two better people than to walk us through today's session. So with that, I'm going to hand it off to Piero to kick it off. Take it away, Piero.
Thank you very much for the introduction, Michael. So let me share my screen first of all, and just confirming if people can see my screen. All right, I think people should be able to see my screen. Yeah, first of all, I'm super excited to tell you guys about Ludwig 0.8, our new release, which includes many interesting things, all sort of LLM related goodies. And again, we're going to get into the details of them, and Arnav is going to show you how to do that in a notebook. But first, I wanted to give a little bit of context about Ludwig first, and how it came to be, and what are the capabilities that are in there beyond large language models, and then jump into large language models immediately after. So the motivation for creating Ludwig was that when I was working at Uber, I was working on many different machine learning applications. And this is like a selection of some of them. For instance, the first one that I worked on was an intent classification model, was written in TensorFlow. There was quite some code, a lot of many months of development, and even more for deployment. This was the first deep learning model that was deployed at Uber. Then there was a new project that was on fraud prediction, was using PyTorch this time around as a code base. And it was somehow a little bit shorter, but still it was about 9 months between inception and deployment. And then there was a product recommender system that was used for Uber Eats. This required even more time because it was even more complex because of the types of data that included images and text and all sorts of multimodal data. And so my suspicion is that there must be a better way to actually do machine learning projects without having to reinvent the wheel every single time and spend all of this time, right? That's the reason why I came up with Ludwig. And what it is, it's an open source declarative machine learning framework that I started when I was at Uber, but then was made open source, and now it's backed by the Linux Foundation. And the way it works is that you just have to specify a configuration file, a YAML file, for instance, in order to be able to define your entire machine learning pipeline. And if you're familiar with Terraform, for instance, what Terraform does for the infrastructure, Ludwig does for machine learning, more or less. What you see here on the left-hand side is configuration, just 6 lines of a configuration, and that's all that's required to match 100% those like 5 months of development that I did on the intent classification model when I was at Uber. All you need to specify is the schema of your data, so what are the inputs and what are the outputs, and what are the data types, and Ludwig takes care of the rest. This is like good because it doesn't require you to write low-level machine learning code if you're not a super heavy machine learning expert, while at the same time being really readable and reproducible. It gives you also all the power that you need as an expert to control every aspect of the pipeline, which includes the models, the parameters of the models, the training parameters, the pre-processing parameters. Everything is basically available as a string in this configuration file. And there's more than 1,000 different things that you can change. So please look at the documentation. There's like plenty of things that you can change, modify, adapt. And iterating of models becomes very easy. Just change one string in the configuration file and you have an entirely new model. And it's also extensible. So if you want to write your own Python classes and give them names, they become referenceable from the configuration. So you can add very easily more capabilities on top of it. And finally, it has advanced functionalities like hyperparameter optimization, state-of-the-art models already baked in, and there's also distributed training inside Ludwig, all available for you from the configuration. And so the effect of that when I was at Uber was that now there were other teams, other people that were other than myself that could write something like 15 lines of a configuration file in YAML. And it took them a day to get to a point where they had like a good model and about a week to deploy it in production. And this was an example of a team that was the website personalization team at Uber. So it was not a team of machine learning experts. So they were mostly engineers. And so this empowered them to do machine learning, really. This was made possible by the fact that Ludwig has this general architecture that can be applied to many different use cases, and it really depends on the types that you choose for your inputs and the types you choose for your outputs, between category, numerical, binary, text, image, audio, and there's a few more like time series and geospatial data. And so depending on the scheme of your data, there's a specific instantiation of this architecture that works for a specific task. And these are some examples. For instance, if you have category, numerical, and binary as input, and the numerical is output, then you have a regression model. Or if you have a text as input and category as output, then you have a text classification model. An image as input and text as output, you can train an image captioning system, and so on and so on. You can imagine that how combining inputs and outputs types makes it possible to train many different types of models, right? So this was already in Ludwig since the beginning and up to version 0.7. In version 0.8, which we released last week, we're adding many new capabilities that are specifically around the large language models with a new model type and new state-of-the-art models that we've been adding to the platform. In particular, the main capabilities that I'm going to tell you about today are prompt templating with both zero-shot and few-shot in-context learning, and how to declarative fine-tune large language models, both with an integration with DeepSpeed and using parameter-efficient fine-tuning techniques. Arnav, after me, is going to show you how to do that in the notebook. So I'm going to try to be fast at explaining you these different capabilities, hopefully also answering all your questions. And I'm happy to take questions also in the Q&A session after Arnav's section. Let's start with prompt templating. So one thing that we added is, again, first of all, the capability to use large language models in Ludwig. And so you can specify in your configuration file here on the left-hand side, both the model type to be LLM and which model do you want to use. For all the examples that I'm going to show you today, we're going to use Llama 2 in the 7 billion version because it's the latest and greatest and best one available right now. And so what you can do is you can specify a prompt that you want to use for solving a specific task. And in this case, the task, we define it as rating a book review with a score from 1 to 5. And so you can specify a template that contains components. One component is the task itself, and the other component is how to use the data that you are providing. So on the right-hand side, you have an example of one row in a data set of reviews where there's a title of the review itself, and a score. And so given the title and the review, we are asking the model to provide the score. If you have a configuration like this, then what actually happens is that Ludwig puts it together into an actual prompt for the model. And the prompt looks like this, where that task variable is resolved with the definition of the task, and the review section is resolved with the contents of the data in your data frame. And basically, you can provide, you can create a new model. On the other side, there's some example Python code using Ludwig's API, where you create your new Ludwig model with this configuration that I showed you. And then you call create model, and then you can call predict on a new data frame, and the results will contain the outputs of the model on that data frame. So this is an example of what I showed you. It was an example of zero-shot context learning, which means you're not providing additional information about the rest of the data set when you are trying to obtain the predictions for a specific data point. But Ludwig supports also few-shot in context learning. What that means is that other than the example input and the task components in the prompt that I was showing you, there is also another part of the prompt, which is called context. And that part is filled with other data points from your dataset. There's a few methods for filling that. The default one is a random one. So you can choose some random subset of the datasets to help the model give the prediction on a new data point. But the most interesting one is actually what we call semantic. And what happens there is that your data points are indexed into a vector store, and then at prediction time, they are retrieved. And so they are added to the context. The most similar ones with respect to the data point that you're providing are the ones that are added in the context. The combined prompt is provided to the large language model and then produces its answer, exploiting this additional information. How does it look? It looks similar. The difference is that if you look at the template section here, there's a task section, there's an example section with this __ context variable, and there's also the part where you can specify the content of your data, like the review, the columns from your data. Additionally to what we were doing before, there is also a retrieval section which decides what is there in that variable context. In this example, we're using this semantic retrieval, and k is a value that defines how many of the data points in the index we want to retrieve, in this case 2. And that model name is actually the model that is used for both embedding and putting the data points in the index and also for retrieving them. So both data points are mapped into vectors, and those vectors are used in the vector store to retrieve the data points. Assuming that we have retrieved data that looks like the one on the right-hand side, because it's relatively similar to one data point that we have, what actually happens is that the input to the LLM becomes, there's a section for the task, the section for the example, and you see that it's filled with the values coming from this retrieved data, and a specific review that you want to obtain the prediction on, and the ask for the model. And the way to use it is exactly the same as previous one. Once you created the model, then you can call predict on it and obtain the predictions. Let's switch gears to talk a little bit about how do you want to fine-tune models. The reason is that both zero-shot and few-shot learning are particularly useful if you want to augment your large language model with information from your data set that maybe was not available to the model when it was trained, right? At the same time, there are instances where that is not sufficient. For instance, if you want to train the model on data that is completely different from what it was trained on, but also like contains different style of language, or maybe has some specific constraints like generating structured information, or like JSON files, or something that is like a little bit more distant from what the model was trained on, right? In those cases, you can use Ludwig for doing fine-tuning. And one example here is doing instruction-based fine-tuning, where you have both examples of inputs and outputs of what you want the model to produce. And in order to do that, the configuration looks like this. First of all, you need to specify once more the model type and the base model, and also what are the inputs and the outputs, basically are the columns in your data set that contains both what is supposed to be given to the model and what you want the model to give out as an example. And you can specify the characteristics of the trainer, which include learning rate, batch size, the gradient accumulation, the number of epochs. There's many more parameters that you can modify, change, and adapt to your use cases if you want. But these are the basic ones. And in order to train a model like this, you just create a model with this configuration, and you call .train on a data frame containing the data. What this does, it trains all the layers of the model, both the encoding part, the embedding part, and the decoding part. But what if you wanted to train a model to work on a specific task that is different than text generation? So for instance, you want to use that model for doing classification, sentiment classification. In Ludwig, it's very easy. All you need to do is to change the configuration a little bit. So the output feature, in this case, you need to specify the type to be category instead of text. And you need to specify an encoder to be exactly the llama model that we were talking about before. And you can set if it's trainable or not. What will happen in this case is that there's a new head that is added to the model, that yellow box that you see in the image. And that head is trained specifically for sentiment classification in this case. And the orange part is what is reused from the large language model that you want to fine-tune for this task. Finally, you can do the same thing, but freezing the large language model. And if you do that, you need to specify, in order to do that, you need to specify trainable equals false. But if you do that, the advantage is that you can also cache the embeddings that are created for each of the inputs. And if you specify cache encoder embeddings to true, what happens is that all the representations are created once only, which makes training substantially faster, like 50 times faster. There's a trade-off, though, between the performance and the speed of training. So if you want to have the best performance, fine-tuning is the best way. If you want to have a model quickly, freezing the weights is a better way. You can pick and choose and make your own determinations. One thing that is important to note is the fact that with these latest large language models, the number of weights has increased to the point where they don't fit anymore into a single GPU. That's been true for a while now, at the very least for the last year. And we integrated with deep speed, which is a mechanism for doing model parallel training, meaning that a single model is split among multiple GPUs. Doing it naively, though, it leads to out-of-memory errors because the way it works is that all the weights need to be in each worker, and only the ones that are relevant for the specific GPU are going to be loaded on the GPU. But again, all the weights are pretty big, and so that already leads to out-of-memory errors. So we did this optimization using this zero-copy mechanism that makes it possible for us to load all the weights only once, and then load on the specific GPU the weights that are needed for that GPU only. In order to use this, it's very easy. In the configuration file, you can just specify the backend section, which deals with how to manage the infrastructure aspects of it. So you can specify that you want to use Ray as the backend, and that the trainer needs to use GPUs, and that the strategy that to be used is deep speed. Deep speed itself has a bunch of parameters, so you can change all of them, like for instance, the stage of the zero optimization and the float of the parameters. So you have all this. It is possible for you to perform that by changing these parameters. And also there's like bfloat 16 optimization that makes it possible to fit more parameters on a GPU because they are less precision at 16 bits instead of 32 bits or 64 bits. And in order to train a model like this, you need just to specify deep speed and no pattern on rank, the number of GPUs that you want to use, and your regular Ludwig command for training, which is Ludwig train, the config, and the dataset. The very last thing that I want to highlight before going into the more fun part with the notebooks is that we also added capabilities around parameter-efficient fine-tuning, and in particular, techniques like LoRa, the LoRa adaptation prompt, and QLoRa. The way this works is that instead of training and fine-tuning the actual model, they have some weights that are parallel to the weights of the model. And there's like a very small number of them compared to the entire model, really. And only these weights are trained, and they basically steer the model into producing the predictions that are more aligned with the dataset that you're fine-tuning on. In order to do that, it's very easy. Once more, in the configuration, you can specify the adapter section, and you can specify the type of the adapter, for instance, LoRa or analora, etc., and the parameters of the adapter, for instance, R, alpha, and the dropout are parameters for LoRa. And if you want to use the quantized version, you just specify quantization bits. It's either 4 or 8. And the advantage of doing that is that it compresses even further the amount of memory that is needed in order for these models to be fit on GPUs. So you can have larger models with more quantization. And there's usually a good trade-off with respect to doing that. The very last thing I wanted to show is one example about you put all of it together for doing like instruction fine-tuning. And so you can have in your configuration the model type and base model, the adapter section, the quantization section, the prompt that you want to use, the inputs and outputs, and also the training parameters. This gives you all the flexibility and the capabilities that you may want for doing fine-tuning. And using this configuration is as simple as Ludwig model configuration and then calling training on the object that you get out of it. All right, so I covered all my section, and I will hand the presentation to Arnav that's going to show you this really fun tutorial.
Yep. Yeah, thanks, Piero. So essentially, the goal for today with the webinar is, or at least with the notebooks, is to make sure that you sort of get an understanding of Ludwig at a very high level. And then from all the new features that we released with Ludwig 0.8, we're going to try and do 3 things. One, zero-shot prompting or templating. The second is in-context learning through the semantic search that Piero was describing. And the third is actually fine-tuning our own Llama 2 7 billion. And also the format of this sort of notebook or walkthrough is that I'm going to share the notebook link with you. You can also access it on the bottom left of your screen where it says Ludwig Notebook for today's session. And I've already run all the cells in advance because some of them take a little bit of time. For example, loading the weights, model weights into memory takes some time. So we'll just walk through the notebook and the outputs. But if you're interested, you can just watch that and I'll share my screen. But in case you also want to see and run these cells yourself, yeah, definitely feel free to just hit Shift Enter on each of the cells from top to bottom, and the notebook should just run. Cool. So let me share. Sorry, one moment. Share a window. Let me see. Okay, so is there? Can I get any visual confirmation that you guys are able to see my screen?
Yes or no?
Okay, thanks. Cool. So let's get started. Hopefully, you're all able to access this notebook. If not, like I said, the links are both on the bottom left of your screen and in the chat. But what we're going to do is a quick walkthrough of Ludwig, and then, like I said, zero-shot prompting, few-shot in-context learning, and then fine-tuning Llama 2 7 billion. And sort of the goal for this webinar is to see how we can use Ludwig and pre-trained LLMs for code generation. And so really what we want to do is take, let me see if I can actually make my screen bigger, is take an instruction in natural language, such as create an array of length 5, which contains all even numbers between 1 and 10. So we want to be able to pass this into the model and then have it generate an array with just the correct response and nothing beyond that. So this is the goal, and there's many ways we can sort of iterate on this journey to get there, from prompting to fine-tuning. And along the way, we'll sort of discuss what we're seeing, sort of the trade-offs, and sort of the performance improvements as you go through each step. So I think Piero already gave you an introduction, but for those who joined late, here's a quick 2-minute introduction to Ludwig. Ludwig is essentially our open source toolbox for training machine learning models such as large language models, general neural networks, and tree-based models through a config. And it's as simple as defining the name of your input features and output features. And this is traditionally all it takes to get a model from Ludwig. And this is how it was done from Ludwig 0.1 all the way to Ludwig 0.7. But in Ludwig 0.8, we introduced two new keywords. Model type has always existed, but we introduced a new type called the LLM model type, referring to essentially large language models. And then there's the base model keyword in this config that you just have to add. And what you specify here is the name of any Hugging Face pre-trained causal language model. So we support everything, Falcon, Llama 2, Llama 1, OPT, the whole farm. And you should be able to use them right out of the box with Ludwig. And once you define this YAML configuration, there's two ways to interact with Ludwig. There's the Python Ludwig model API, for which I've linked some docs here. And there's also the Ludwig CLI. For this webinar, I've decided to use the Python Ludwig model API just because I prefer to interact with Ludwig that way. But Ludwig also has a CLI, and the API, the Pythonic version and the CLI version have feature parity, so you can use whichever one you want. But this is all we need to know to actually sort of dive in to try and solving the goal that we have today. So there's some quick basic setup steps that I ran through, which was installing Ludwig and Ludwig LLM related dependencies. I installed from Ludwig master just because I wanted some additional commits, but it's as simple as just doing something like pip install Ludwig, and then pip install Ludwig LLM. So just doing that should work and get you there. This is just using a pre-release version. And then I have some code here just so that we can see the outputs a little bit better, as well as clear our CUDA cache. One thing I would highly recommend if you're running this yourself is actually connecting to a GPU. And by default, like on Colab, there's many options, but on the free variant, you get CPU and T4 GPU. The T4 GPU is not always available. So if it's not, I would recommend maybe trying to run it at a different time when it is available, because it definitely significantly speeds up every single part of the LLM process. But yeah, for me, I just connected to a T4, which was sufficient to get through this entire notebook. The next thing we want to do is set up your Hugging Face token. I saw a bunch of people in the chat talking about the Llama 2 model and running into some errors here. So the the background is that Meta released Llama 2, which is sort of like the new generation variant of the original Llama model, which was released back in February or March this year. But the model is gated, which means you actually have to request for access and they have to grant it to you. It's usually a very quick process. You just have to click into the link here and then request for access, follow some steps, and you'll be able to use it. And once they give you that access, just adding your Hugging Face token should let you use Llama 2 with Ludwig. And this is not unique to Ludwig. This is any framework using transformers and Llama 2, you'll have to do this step. So yeah, I configured this in advance. And the next step that I did was import the code generation dataset. So this is, for those of you familiar, it's a variant of the Alpaca dataset, which is an instruction following dataset. But this one has natural language as input and code as output. I'll show you what it looks like in a second. And I have some code to insert an additional column called split that basically assigns 3 unique numbers, 0, 1, and 2. 0 to indicate the data is in the train set, 1 to indicate the data is in the validation set, and 2 for the test set. This isn't that important now, but it'll make sense as we go through the rest of the notebook as to why I added this. But let's take a look at the data itself. So this is a quick snapshot of the first 10 rows of this data set. You can see it consists of 4 columns. There's the instruction column, which is a natural language input, such as create an array of length 5, which contains all even numbers between 1 and 10. There's an input column, which I will come to in a moment. There's the output column, which is the expected response that we want the model to produce, either through prompting or through fine-tuning. In either case, this is the goal. And then there's the split column, which, like I said, we'll also discuss later. And this is actually, one thing I want to call out that you can see here is that some rows of data have an input specified, and some of them are just blank. And this is actually by design. And I can talk about that a little bit further. So the first type are the self-sufficient type of instructions. What this means is that the instruction, the task that we want the LLM to do is self-sufficient in that it has all the context for the LLM to be able to respond to that instruction. So this, I've said this example 3 times now, but this is a really good example of, a self-sufficient instruction that is good enough for the model to produce a response. And it's really helpful for things like coding tasks, mathematical calculations, data manipulation tasks. That say you want a natural language input to convert, do some pandas operations for you. Usually you don't need to provide additional input as context, writing instructions, things of that nature. But the second type of data point in this table is one with, we're going to call it those that need context. And so essentially it augments, it gives more context to the instruction. For example, here we're saying write a replace method for a string class, which replaces the given string with a set of characters. Now, there's many ways of implementing something like this, right? It could take different arguments. There's many things that we can do. But when we provide input as additional context here, such as string is equal to hello world, replace with is greetings, what it tells the model is that, oh, those are the 2 arguments, that maybe I need to pass into this function that I produce. And so, there's also these styled sort of inputs in the data set. And they're really good for things like, customized code generation, conditional responses. A really good example of a conditional responses, you're asking your program to figure out, what letter grade to assign a user, and you define the criteria in your instruction. And in the input, you actually give it sort of like the score, like 85 and 100, assign it to a grade. There's dynamic content creation, configurable process. There's so much you can do. But between these 2 types of tasks or 2 types of rows, there's a breadth of things that you can do. And one thing I wanted to highlight is that even though I've sampled just 100 rows of this data set, in general, there's the split between instructions that have an input and instructions that don't have an input, it's about 50-50, which is good because it helps create a fairly balanced model when we fine tune. The other thing that's really important when you're thinking about LLMs and looking at your data set is what is the sort of length of the input in the output in terms of the number of characters. And the reason for this is because the way all of these large language models work is that they're trained on a context window or a fixed size of the number of tokens that they can take as input. And for Llama 2, for example, it's 4,096 tokens. For those of you who aren't familiar with the word token, they're essentially, think of it as like chunks of letters or characters that are passed into the model. So your input is converted into these smaller pieces called tokens, and then that's what's passed into the model. And so one thing, usually this is a very like ballpark estimation, but every 3 to 4 characters typically maps to a token. And so what we can do is look at this data set and say, well, what is the average number of tokens in each of these columns? And also take a look at this histogram. So we can see that on average, 23 for the instruction, 8 for the input, but the outputs can be pretty long. It makes sense because we're generating code, which definitely involves a lot more output than for a natural language input. And other things that we can see is that quite a significant chunk of examples, like over 50%, like I was saying, or around 50% have, no input tokens, like for the input column. The instruction is sort of varied, but like average length around 60. Very few instructions that are very long. A lot of them are shorter. And so this is really useful. The primary reason is obviously to understand it, but it's to make sure that whenever you're prompting LLMs, the context window is enough for your input to like not get truncated or cut off when you're prompting. A lot of these models also complain when you pass in more tokens than they can actually process. So in this case, what I wanted to highlight was Llama 2 can take 4,096 tokens. We're well under that range, so that's good to know. Cool. So now that we know roughly what a basic Ludwig config looks like for LLMs and the task that we're doing, as well as what our data set looks like, I think we can dive into some of the Ludwig features that Pierre was talking about, starting with prompt templating and zero-shot inference. So to give you some more background, in case you're not familiar, when a lot of these large language models are generally trained on data across the web, and there's many mechanisms to train them, but one of the ways is predict the next word and then do that over your entire data set. But in the process of doing this over so much data, they actually inherently have some knowledge about topics and a lot of different things. And so what zero-shot learning is essentially, it's what we call an emergent property of large language models, where you can prompt them, and then they can actually answer questions that they might not have actually like been explicitly trained on or learned about. If you've used ChatGPT before, when you prompt it and you give it some information, it's basically you're doing zero-shot inference. ChatGPT wasn't actually trained to answer those questions. It's using pre-trained knowledge to answer those questions. So very powerful model. And here's a quick example of what this looks like. So you have a prompt, you give it this thing, you have answer, and you say, well, give me an answer. If we want to do this in Ludwig with an open source LLM, it's actually very, very simple. Or on your custom data set, we have two keywords that we define. There's the prompt keyword and there's the generation keyword. So the prompt keyword helps us define, as Piero was showing in his slides, the task that we want the model to perform. And there's many things that you can do with the prompt. I won't dive into this here, but I'm leaving this here for information. I think it's best understood if you look at the example below. And then there's generation, which is essentially a way of controlling how you want the model to produce tokens. For example, how many words should it produce? Do you want the output to be very diverse, or do you want it to be, less creative and more, determinist? I guess like more sure of its responses. There's many generation parameters as well. I've linked to the docs. But if you want to combine this all together to see how the model would do out of the box for this task, let's take a look at this config. So like I said, all Ludwig needs is a config, and then we pass it to the Ludwig model API. We have a model type as LLM, base model as Llama 2.7 billion. Our input feature is instruction, because that's, as we saw earlier, like that's what we want the model to, what we want to pass to the model as like an input. And the output feature is the column called output from our data set. The two things to focus on here, like I said, are prompt and generation. So let me highlight those. Let's talk about prompt first. So under the prompt, there's a notion of task and template. And in the template, you can essentially define your instruction. There were two options here. I could have just, passed in the instruction as is and had the model and asked the model to produce an output. But typically, there's a really nice paper on the fact that a good prompt that's very clear and that directs the model towards what you want it to do, really helps the model in doing the task that you want it to do. So I was pretty explicit in what I wanted it to do. Below is an instruction that describes the task paired with an input that may provide further context. The reason I use may is because some examples don't have an input. And then write a response that appropriately completes the request. And then I pass in these really funky looking instruction and input keywords like this in these curly brackets. And all this is basically doing is taking, for each row of data, it's going to take the data from the instruction column, put it into this prompt. It's going to take the data from the input column, insert into this prompt, and then pass this entire template to your large language model. And then the large language model from there will produce some output. There's also generation, where we can control many parameters. The two I really like to use, and I think that greatly influence the output quality, are temperature and max new tokens. So max new tokens is very self-explanatory. It's a number of new tokens that can be produced, or that you want the model to produce. When you set this number, it doesn't mean it will produce that many tokens. It's the most number of tokens we're forcing the model, like we're allowing the model to produce. And temperature controls sort of, the randomness of the predictions. So higher temperatures mean more creative, more diverse outputs. Lower temperatures tend to lead to more, I won't say deterministic, but it's because it's not, but essentially outputs that are less creative and more objective. So we can ignore these for now because I'll come back to them. But all you do is you take this config, you pass it to your Ludwig model API like this, and you call model.train. Piero showed a different method. There's two different ways to do it through Ludwig. One thing I want to call out is that we're not actually training a model here, but we're just doing some evaluation on it. And so let's take a look at the Ludwig output that I ran in advance. And hopefully if you run it, you'll see pretty much the same behavior. So the way Ludwig works is it pre-processes your data. So it takes our inputs and it tokenizes them. And there's many pre-processing parameters that you can control per feature, loads the model into memory, and then actually performs evaluation. So here's an example of an input, right? We've seen this a few, that was passed in the model. with the prompt. So below is an instruction that describes a task paired with an input that may provide further context. This is our template. You can see that it actually inserted the instruction into the data set, into this prompt. So create a JSX code, slightly wrong English, but that renders a hello world message in the browser. And then it's input, and then there's response. And what we want is the model to continue generating a response from here. And then if you look at what the model does, you'll see that it just repeats itself again and again and again and again and again. Initially, I thought this was a bug, but it turns out that the base llama model is actually not very good at following instructions. In fact, when it gets confused, it tends to just regurgitate the input that was passed into it over and over and over again. And this is pretty common across a lot of the examples that you'll see here. That being said, I do want to show equally an example where the model, to show you that llama is not the worst model out there, it's actually very good, even in the base state. Here's another one where we pass in this instruction saying, write a function that takes in a list of numbers and prints out the greatest number. And we wanted to produce a function. And if you look at the decoded output or the generated output, you'll see that it actually partially understands the notion of what we wanted to do. It does pick the greatest number, but what we wanted it to do was write a function to do this for us. So directionally correct, like good intention, but the output isn't quite right. And you can go through all these examples, but essentially the behavior is roughly the same. And I sort of summarize it into this observation section here. One is that the base Llama 2 model can produce very coherent English, which is good. It's a sign that it understands grammar, it understands semantics, it understands how to do those kinds of things. But when it doesn't know how to respond, which seems to be a lot of the times when we ask it to follow an instruction, it just returns the input over and over again, and it does it until it hits the max number of tokens. It doesn't know when to stop producing a response. And in an ideal world, the model has learned or knows when to stop, right? It produces like a list or a function and then stops right there. And it didn't get a single one of these input prompts correct. And to me, none of these results are surprising, because while it shows that Llama 2 models can be good on very general tasks like what is the capital of Italy, or where is China, something like that, they're not very good for domain-specific tasks out of the box. That's when they just use pre-trained knowledge without any additional context. So another sort of follow-up emergent sort of capability that comes with large language models is this notion that it's called few-shot learning. And it's this idea that if you give in the prompt, if you give it a few demonstrations of how to do the task, and then ask it to do your task, it has a higher chance of producing better responses, because it starts to basically understand the notion of what you want it to do. And so it's called few-shot learning. And the idea of a shot is just that's just a fancy term for a demonstration. So I think this image sums it up really well, where you have demonstration 1, demonstration 2, and then we actually ask it in the same format, like can you do the third task? And to go from zero shot to few shot learning, as they call it in Ludwig, is really simple. You can just modify your template and add a couple of instructions. So here I've just added this. Here is some context, here are some demonstrations, and then the same template, and it'll just do few shot learning for you. I didn't think this would be that fun to do, so I didn't actually put some code snippet, but you can feel free to try it. All you have to do is change the template. The one thing I do want to call out about few shot learning is that if you hard code these kind of responses, they might not be always relevant to the sort of dynamically changing instructions, and they don't always cover every variation of the task. So there are a lot of limitations to few shot learning as it in like the static form. But a big thing that's very popular these days is retrieval augmented in-context learning. So what this is essentially a variant of few-shot learning, where instead of hard coding some demonstrations, we can dynamically insert relevant demonstrations into the prompt per task. I have like an architecture diagram in case you're curious on what's actually happening. But really, beneath the surface, what we're going to do is you have something called an embedding model, which takes in text as input and produces an embedding, which is essentially a representation of numbers that represents the semantic information of the text. And so what we're going to do is we'll take a chunk of our data set, we'll pass it to this embedding model, and we'll save it somewhere. And then when we pass in a prompt, let's say, create a list of the first 10 numbers, we can actually go to this embedding database, a vector database, pull out the most semantically similar examples, dynamically insert them into the prompt, and then pass that to the LLM. And I'll show you what this looks like in Ludwig in a moment. But again, to go from zero-shot to few-shot learning is very, very easy. In-context learning is very easy in Ludwig. We can take everything we had before, but the main thing we now add is this new keyword called retrieval nested under the prompt. It defines the way we want to do a retrieval strategy. So in this case, Ludwig supports two, random and semantic. We'll do semantic retrieval, which is this idea of using a vector database or embedding database with some data and then dynamically retrieving it at inference time. You can pass in any embedding model from the sentence transformers library. I've left a link here so you can see the whole list. This is just one that's become pretty popular lately. And then the number of examples to insert, which is done through this parameter called k that Piero had also mentioned before. For demonstration purposes, I just use k is equal to 1, but typically you want to insert at least 3 to 5. The other modification I made is that in the template, I added this new piece called context. So you can see that this is slightly different from instruction and input. It has these underscores. It's a reserved keyword, and it's only for few-shot learning, where anything that's returned from the embedding model is inserted right here. So to take a look at some outputs, or just to show you what it's doing, and this is the main takeaway I want you guys to have on how easy it is to do. When you run that config with Ludwig, say this is so we've already seen this input, right? Create a JSX code that renders a hello world message in the browser as the instruction. But let's take a look at the part just before. So we have, here is some context for the task below, 3 pound keys, and then this list with an example from our data set. So what's happened is the embedding model was used to return the most semantically similar example from our training data, insert it into this prompt, and then pass that in as well into the LLM. So this is the entire input that was passed in. I use k is equal to 1 just to show you guys you want to use 3 to 5. But what I also want to show you is that with just one shot, Llama still did the same thing as we saw with zero-shot learning, where it just regurgitates the response. And this is kind of true across all examples. Now, what I do want to say is that actually RAG, or retrieval augmented generation, is actually a very, very powerful technique. And it's used a lot these days, pretty much across any company or anyone using vector databases like Pinecone, Milvus, and so on. In our case, for this task, with k is equal to 1, it didn't work so well. It actually behaves very similarly to zero-shot learning, which is fine. But what the highlights are, I showed you that you can use this embedding model to dynamically retrieve examples from the data set. Just had to add 3 new lines of the config to the config. And here are some reasons why this might have not worked so well. I remember I'm only using 100 rows of data, of which 90 are or 88 are in the train set. So it's a very small sample size to retrieve from. But the actual data set has about 18,000 rows. So I'm sure that if you were to use the full training data set, we would actually find much more relevant, semantically similar examples. I use k is equal to 1, which was obviously too small. You can use a different embedding model. You can also write a much better prompt. But in my opinion, this task is just too hard to solve through regular prompting, and it actually requires something even more important. And so this brings us finally to my favorite part of this webinar, how Ludwig helps you declaratively fine-tune large language models. For those of you who are not familiar with what fine-tuning is, so far what we've done is we've taken this pre-trained model that someone else trained, we've just prompted it to produce outputs. But with fine-tuning, what we're going to do is actually using our data, we're going to use our data to update the weights of the model and basically teach it how to do our task. So in case it doesn't have knowledge, which is also true in the case of zero-shot and few-shot prompting, here we're actually going to teach it over some data and then use that for predictions. And the task, and sort of the fine-tuning process that we're going to see is called instruction following or instruction fine-tuning. Piero had mentioned it. It's just the fact that we're going to pass in these instruction and output pairs in our domain, which is code generation, and then update the weights to do that. And so the goal of this fine-tuning process really is, when we use the base model for this simple instruction, we saw that it produced, like, it just kept repeating the input that we passed in over and over and over. But what we hope will happen after we fine-tune is that it will produce just the output that we want. So yeah, that's the goal. And in Ludwig, there's many different fine-tuning strategies, but the three sort of that I want to highlight as like a sort of approaches to fine-tuning are full fine-tuning, parameter-efficient fine-tuning, and quantization-based fine-tuning. They're not all mutually exclusive. Like they can be combined together. But I do want to quickly, maybe in 30 seconds, describe each one of these. So full fine-tuning updates all the weights in the model. It's it usually leads to the best performance, but it's very expensive to tune because you're updating all the weights, and these are like in the billion parameter model ranges. It's resource-wise quite difficult to do. You need deep speed and all of these other things. But there's a major risk, which is catastrophic forgetting, where since we're updating all the weights in the model might forget some of the knowledge that it gained during previously being trained, during the pre-training phase. So that's full fine-tuning. It's pretty traditional. Most people tend to do this. But then there's another variant called parameter-efficient fine-tuning, where you just update a few weights in the model or insert a few new layers, which are trained, but the rest of the model is kept the same. And this is like very computationally efficient. It's really fast. Usually doesn't lead to catastrophic forgetting, but it may sacrifice some general performance compared to full fine-tuning. So if you've heard of LoRa or add a LoRa adaptation prompt, like these are a different PEFT or parameter-efficient fine-tuning strategies. And then finally, quantization, which basically is just a way of representing your model weights in integer format. Normally, they're represented as floating point. Don't want to get into too many details, but the biggest takeaway here is that it helps you reduce the amount of memory you need by sort of like reducing the precision of the parameters in the model. And so you can go down to up to like 8 times smaller model by using quantization. So really fast, really easy to fine tune. Obviously, because you're reducing the model weights, you're giving up some performance. But really good to do this for like resource constrained devices. And today, since we're training on a single T4 GPU, which has 16 GB of VRAM, we're going to do quantization-based parameter-efficient fine-tuning. So we want to combine method 2 and method 3 together. And to do this is very simple. In Ludwig, you have 3 new keywords that you can add. Adapter, so there's 3 new keywords. There's adapter to specify like which parameter-efficient strategy. There's quantization, which we had seen before, but it's basically use weights in integer format instead of floating point format. And the third is this trainer, because we're actually training a model where you specify the type as fine-tune. You can control all of these different learning parameters, so I won't dive into it, but the main ones, batch size, learning rate, optimizer. And then, as always, just pass into the model, and this will start actually like fine-tuning the model for you. What you should expect to see typically is that your loss after each epoch of fine-tuning is decreasing, at least on your validation set. So this is epoch 1. And what I did is I just fine-tuned, and I want to be very clear, I just fine-tuned 100 rows of data for 5 epochs, which is nothing. And it just took 4 minutes to fine-tune. As you can see, between epochs, like validation loss is decreasing, epoch over epoch. So at the end, we get this training report that says, our best model validation loss was this and test loss was this. Cool. So we have this fine-tuned model. And I think Piero described in depth like what fine-tuning looks like. But the real question is, did it help us actually solve the limitations of zero-shot and few-shot prompting? And so what I did is I took a bunch of examples from the actual training data set, as well as some that I added myself. And all you can do is, now that the model is fine-tuned, you can call model.predict and pass in this data frame of input-output pairs. So it's the same format as the data set we trained on. And then we can see the output. And what's really, really cool that I want to show you is, let's start from here, is that just 100 rows of fine-tuning, which took 4 minutes to fine-tune on a T4 GPU for 5 epochs, actually starts giving us very, very close to perfect responses. So if this is the instruction, look at this response. It said CERP, not sure what that is, but it actually does produce 2, 4, 6, 8, 10, which is awesome. Create an array of length 15. Again, I think it's learned somehow because it's limited amount of data that's here is array. But the point I want to get across is it actually gets a list of the numbers that we want. We can have it do more complex things, such as create a nested loop to print every combination of numbers between 0 and 9. So it defines this list. Not sure why it's not needed, but yeah, essentially, it's printing out every combination of numbers in a nested for loop. This will do the right thing. Compute the sum of numbers, everything about this is correct. Create a class to store student names, ages, and grades. So a lot more complicated now. And you can see that actually this is correct. This is actually very good. And finally, you can even have it like print out dictionaries and things like that. So what I want to show you is, because we fine-tuned this model, even using such little data, we're actually able to produce near perfect output, which is awesome. Of course, it's not all perfect. Things like CERP and things like that should not happen. CERP bounded up by. But if you use more data and fine-tune for longer, it will lead to the right thing. Two things, just to wrap up here. Two things is that if you want to do LoRa or full fine-tuning yourself, you're going to need a lot more compute. A single T4 will not cut it because you're using larger models without quantization. And so you're going to have to use deep speed. And as Piero had already shown you before, you can just add this to your Ludwig config and it should just work. You typically need, I've also mentioned it somewhere, but you typically need about four GPUs with 24 gigs of GPU RAM. If you're an AWS user, that's like a G512X large instance. But if you're okay with QLoRa fine-tuning, you can do it on a single GPU with a 7 billion parameter model. And in case you're curious, doing LoRa and full fine-tuning, as we know, have advantages, but it's very, very hard to do because, it's distributed training using deep speed, figuring out the right compute, making sure your jobs always work. That's the kind of problem that Predibase solves. So Predibase is a managed solution on top of Ludwig that solves a lot of these problems for you. I left some resources at the bottom, and maybe we'll talk about it in a moment. But once you have a fine-tuned model, the last thing that I'll just show you is that you can upload your trained model artifacts to Hugging Face directly through Ludwig, through this Ludwig upload command. And yeah, in case you want to see a full fine-tuned model on the same data set that we trained at Predibase, I actually uploaded the model weights here. So you can just click this link, check it out, and you can use it this way. And then left some resources, but definitely try Predibase. I think it solves a lot of the challenges with fine-tuning larger models, which usually lead to better performance without QLoRa quantization. And yeah, hopefully that webinar was interesting. I'll stop here and then pass it back to Michael for Q&A.
All right. We have a few minutes, so we'll just kind of jump through some of the questions that came in early on. There was one just about, does Ludwig, support specific LLMs like Private GPT, or maybe just talk briefly about sort of the support for different models?
Yeah, happy to take that. So the way Ludwig stands today with 0.8 is that we support every single causal language model on Hugging Face Hub. I believe, from my understanding, Private GPT, it was a repository to take your own data and then, I don't know if it's a fine-tuned model or just prompting, but then use that for your own work. So I don't think it integrates directly with Private GPT. But that being said, you can pretty much use any state-of-the-art open source language model with Ludwig.
Great. And I saw Piero, you had an answer in chat, but maybe to reiterate, someone was asking about, do you need to reload the LoRa weights every time you want to run inference?
Right. So the answer is yes, but Ludwig takes care of that for you, right? If you train the model using LoRa and you saved it, then you can call load on that model, and the LoRa weight will be also loaded accordingly, right? So Ludwig takes care of it. Those are additional weights that you need to carry around, but Ludwig makes it easy for you. Like, you don't need to think about it.
Yeah, and also loading LoRa weights is very lightweight. It's like in the matter of like a few seconds, so it's never like too big of a cost.
Got it. So I want to ask just about like CI/CD workflows and building and testing on generative models, and if you had any just general thoughts around that, Piero. I know you should respond, maybe give your
I would say there's no silver bullet on that. I think the larger point, there's a few larger points that maybe are worth sharing. Are one, first of all, obviously these models are large, take relatively some time to load, and also having them as part of a CI/CD process, can make the process pretty slow, right? And so it's a trade-off, right? You want to get to a point where you don't slow your process too much, but at the same time you cover as much testing as you want using them, right? In between way that we adopt ourselves is to usually use smaller models in the CI/CD, and then have just a smaller number of tests for the larger models, which kind of it's a compromise though. But that may change depending on the use cases and depending on the specific types of models and how big they are that you want to use. The other aspect is obviously there's a new dimension, if you want, of correctness, because these models, it's true for every machine learning model really, but that may or may not be part of what you're actually testing for. And new releases of models can change things that before where models were answering correctly now may not be answered correctly anymore, and other things that were wrong before now can be correct. And also there's a notion of it's a graded level of correctness. Like two things can be both correct. Two answers from two different models can both be correct in different ways. And so that is like a new dimension that we need to account for. There's no silver bullet yet about it.
Great. And maybe one last question, speaking to some new features coming. Someone was asking about support for fine-tuning for increasing the context window, and how you could easily have task-specific fine-tuning that inputs that might be more than 4,000 tokens. What's our thoughts there?
Yeah, Arnav, you want to talk?
Yeah, I can take that. So actually, yeah, Ludwig's 0.8 has capabilities for that as it exists today. The way context lengths are usually increased is through something called rope scaling. This isn't true for every type of model, but any model that uses something called rotary position embeddings. Let me send you a link to the docs, but it's as easy as adding 2 more lines to your config.
Also, that's actually interesting for me because I answered, it was a question from Dragos. I answered it was the next thing we were going to working on. So I didn't realize that the PR already made it in 0.8. So that's actually great.
It's already in.
So it's already there, Dragos.
Yeah. And we've actually fine-tuned a couple of models internally at Predabase that do rope scaling. Typically, we've seen that actually even leads to better performance at times.
Awesome. Any final thoughts from our two presenters on future of things we're doing with Ludwig from a fine-tuning or other capabilities perspective that you want folks to know?
I would say, this is like something that we are focusing on specifically, and the goal for us is to try to make it as easy as possible for you to train and fine-tune your models with Ludwig. And we would really want to have your feedback. Please try it out and join the community and give us your feedback, because we want to make it work specifically for you, right? So the more people use it, the more we can improve it, right? So looking forward all the feedback from you guys. And also if there are specific features that you will want to see in the next release, just let us know. We are looking forward to your feedback.
Awesome. And I just pasted a link there real quick for folks who want to join the Ludwig community. I would love to have more folks, join us and participate and contribute. And thank you again to our awesome presenters. Thank you for everyone who joined. We also shared a link to Predabase if you want to give it a spin. Instantly deploy your custom LLMs on managed infrastructure that scales reliably. You can try that out as well for free. And just thank you, everyone. And the recording will be up shortly. And we look forward to seeing you at our next webinar.
Thank you so much.
Take care, everyone.
Bye.